Good morning, good afternoon, good evening, and welcome to my post on LIGO, the Gravitational Wave Observatory. This is not just a post for physicists, this is a post for people from all disciplines, sociologists of science in particular, and journalists. I think this is something that journalists need to take a look at. It's called the Schumann Resonances, and it's not going to be overly technical. So LIGO, or LIGO, is a multi-billion-dollar gravitational wave observatory, and it recently won its project leaders a Nobel Prize. And most people reacted with approval, but there was a tiny vocal minority that complained about the flaws in the experimental design. They said that the experiment had not measured gravitational waves at all, and that the whole community was not paying attention to critical details. Almost 3 years later, popular scientists like Sabine Hossenfelder are finally beginning to pick up on what these sorts of dissidents have been saying since the beginning. Whereas they initially, despite initially acting as a cheerleader for the results released by LIGO, people like Dr. Sabine Hossenfelder are finally admitting that we have no way to distinguish a deep space gravitational wave signal from something more terrestrial in origin, something that's coming from the Earth or the Sun. It's just not possible. And that none of the attempts to correlate gamma ray bursts with gravitational waves have been particularly successful to date. That means that gravitational waves have not really been detected. The scientific method requires that you make a prediction and then observe that thing happening. And they have not done this. They are writing down what they want to see and then going back through old data to find that. That is not a prediction. It is a post-diction, and it is not scientific. The scientific method requires that you look at all of the data you gather and compare that to your prediction. They have also not done this. They are writing down what they want to see and then throwing away all of the data that does not look like what they want to see. That is not scientific. The scientific method requires that you are looking for a specific effect. If the effect you are looking for can look like almost anything, as in it can have a wide range of properties so that you can see it in random data and fit a curve to that data by picking and choosing what you want to see, that is not scientific. LIGO has been doing all of these things, and I've been writing about these issues on Quora, for example, since the first results were announced back in 2016 and 17. But I differ from people like Dr. Hossenfelder on one key point. She thinks that while LIGO has been sloppy in their execution of the experiment, she thinks that the fundamental experimental concept, the fundamental experimental design is valid, because she believes that light responds to gravitational waves at a different rate than matter. And I think this is an assumption, not a fact, and that this is yet another way in which the experiment is not scientific. In fact, historically, gravitational waves are composed of light. It's just, they're two sides of the same coin. When LIGO announced that they had confirmed Einstein's theory of general relativity by using general relativity to interpret their data, I saw unscientific circular reasoning. Yet people like Dr. Hosenfelder have been trained to believe that if a measurement fits into a self-consistent framework, then it confirms that framework. I don't think that is scientific either, but many people seem to have forgotten this sort of principle of the scientific method. If those who designed the experiment knew that it had all of these flaws, yet they deliberately hid them within a tangled web of complexity, I think that they are guilty of fraud and that LIGO is scam science used to milk billions from gullible politicians. Sabine Hosenfelder, of course, does not go that far in her accusations, nor does she object to the theoretical assumptions upon which the experiment is based. I waxed hyperbolic on these theoretical and epistemological matters in a previous post on LIGO, but in this post, I'd like to focus on more down-to-earth technical problems with LIGO. As usual, my underlying theme is why smart people are often stupid, and that scientists are often not as smart as their public reputation suggests. They very frequently overfocus and miss the forest for the trees. So, something that might be taught, that we've known for centuries perhaps, is, well, let's not go back so far. Let's just say we know that the Earth is shielded from the charged particles of the solar wind by the spinning of its core and the magnetic field that the core produces. Yet this protective force field is not a static thing. It breathes and oscillates, and every time lightning strikes, it sends out an oscillation which can be detected around the world. This is called a Schumann resonance, and the gravitational wave detector, LIGO, is extremely sensitive to them. They look just like what LIGO claims to measure, black holes colliding in distant galaxies. In more abstract terms, Schumann resonances are extremely low-frequency spectrum peaks in the Earth's magnetic field. They are generated and excited by lightning discharges in the cavity formed by the Earth's surface and the ionosphere, and there's a sort of feedback loop between them and the tides. So it's a bunch of oscillators, waves, all adding together. You don't think that lightning strikes in the same place twice? Well, think again. Lightning loves mountain tops, lightning loves colliding air masses, lightning loves places with an intense magnetic field. That is why the Schumann resonances are not completely random. Schumann resonances are the main background signal in the part of the electromagnetic spectrum from 3 Hz through 60 Hz. They appear as distinct peaks around 7.83, 14.3, 20.8, etc., with an amplitude of around a picotesla, orders of magnitude smaller than the Earth's magnetic field, which is about 30 to 50 microteslas. And LIGO attempts to measure changes of 1 part in 10 to the minus 21 within a bandwidth of 10 Hz through 1000 Hz. And the Schumann resonances overlap with the very signal in which they want to measure. And the signal they want to measure, they claim, is composed of interstellar cosmic gravitational waves caused by colliding black holes and neutron stars, which are theoretical objects that, when I was a kid, were thought of as like unicorns. They're inventions of a theory, but they're not things that we can say for sure that they really exist. Yet things have gotten so weird today that whole communities just believe that they exist because they've been talked about by so many people. It's like talking something into existence. It's bizarre. But that's a less technical issue. It isn't necessary that LIGO directly detects Schumann resonances for their data to be polluted and unusable. Small fluctuations in Schumann resonances can cause amplitude and phase shifts of the power grid, to which all of LIGO's sensitive equipment is connected. LIGO is extremely sensitive to fluctuations in the amplitude and phase of the power it extracts from the electrical grid, and while they carefully measure amplitude changes, they are unable to measure frequency and phase changes because that would not be technically feasible with the accuracy they require. One research group looked at LIGO's first detections and immediately saw a correlation with a shift of the US power grid phase. Since LIGO can only claim to have measured a gravitational wave if they rule out such terrestrial or solar sources, they must take these issues seriously, yet they didn't. They ignored the criticism and claimed that the engineers who had looked at their experimental design simply didn't possess the specialized complex knowledge to make an assessment of their system. The article by the engineers centered around the argument that the 32.5 hertz noise is generated by some kind of oscillator with a resonance frequency close to 32.5 hertz, which is powered by a 30 hertz signal, resulting in a low frequency modulation of 2.5 hertz, which is what LIGO measured. Obviously, this 30 hertz power source is a subharmonic signal from the 60 hertz power source grid, which is a noise signal that is so loud that every experiment I've ever worked on in physics has had a hard time making sure that it did not affect their data. It's really hard. If you're doing a sensitive measurement of something, it's really hard to figure out if you've measured something or if the air conditioner just flipped on. But in the publish or perish world of academic physics, anything is going to be reported as a measurement if it seems to have shown up a couple times. So 60 hertz noise is always huge, and subharmonic resonances are common, regardless of power conditioning, and you can easily excite a resonance in a broadband oscillator by stimulating it away from the peak of the resonance curve. So when I looked at the noise power spectrum and saw how broadband the 30 hertz subharmonic was, the engineers claim that the subharmonic excited a broadband oscillator with a 32.5 hertz central frequency made perfect sense. The last claim that they made was that the 30 hertz subharmonic noise could easily be produced at two locations. Oh, I didn't write that correctly. That what LIGO detected, this noise, could have easily been produced at two locations by slight frequency shifts in the power for the experiment. The connectivity of the US power grid was concerning enough to LIGO that they decided to collect amplitude data on the incoming power, but the valid complaint of the author of this paper is that LIGO neglected to collect frequency and phase data. So, I mean, that's almost impossible to compare two sites that are so separated by such a large distance. And this is a legitimate criticism. I have a solid grounding in synchronization issues in that I wrote my thesis on laser-based femtosecond synchronization systems. And I have an article on how sensitive those systems are to changes in the pull of the moon, on tidal changes, and how you can compare this to measurements from LIGO. And I encourage those with a technical background to look up that article. It's I think I filed it under posts deleted by Quora. So whenever I would post something that I think people really liked, sometimes people would report it so that they could try to steal it, and it would disappear, and then I would have to copy it and put it on my blog. And then I'd ask Quora to put it back, and they would, because it had been deleted for an illegitimate reason by someone who just, I don't know what they were doing. But that's a worry too. With the internet, you can, if you're posting on a public website that's moderated, people can complain about your post, and so that it gets removed, and then they can go take it and publish it elsewhere. It's really the Wild West. Okay, I'm not going to talk too much about the power grid, but the experiment is extremely sensitive to any changes in the power grid. And it's sensitive to man-made changes and to local geologic events like sunspots and Earth's magnetic field changes. This illustrates the basic problem with the LIGO experimental design. There are simply too many uncontrolled, local, coincidental sources of error, and they have to rule out all of them, even the rare ones. And while they have a small army of people who are dedicated to this task, you couldn't make an army big enough to do this task. You'd never be able to be sure that you've gotten every single source of error sorted out. It's an impossible task. And yet that is what the experimental design is based around. It's smoke and mirrors. It's a scam. And people who are hired by the project blind themselves to this because they're getting a paycheck. So this wasn't the first time that the experimental design, this paper, was not the first time that the experimental design had been criticized on these grounds. I remember hearing such criticism when I was just in college, back when the experiment was just starting. But over the years, the critics got used to being ignored, and they lost interest. Meanwhile, instead of concluding that power grid phase shifts make the experiment impossible, LIGO people turned a blind eye and soldiered on for 3 decades, until those who had objected to the experiment on technical grounds either lost interest or they died. In a sense, their experiment was successful because it continued to secure new rounds of funding, and the project leaders won lots of awards after a great announcement of success. Their PR operation was on point, and they rallied a great audience of science fans with the help of prominent pop scientists. Real scientists are much more skeptical of things like this, and despite a political effort that secured funds to build another gravitational wave observatory in Japan, Japanese scientists saw that the experimental concept they'd been sold was trash. Instead of spending the allotted money and wasting the time and energy of a small army of young, myopic scientists who can be trained to focus on their narrow, ant-like roles without questioning foundations, they politely canceled their facility, much to the Americans' dismay. the reason that the Japanese scientists gave was that they could not successfully isolate their sight from Schumann resonances. So I had a link to that paper, and I'm not seeing it right now. This was true a few months ago when I wrote this article, and I had a link to the paper by the Japanese scientists, but I don't know what happened to that right now. And that's disturbing that the link is gone. Maybe the politics are going back and forth and they're still bargaining with the Japanese, so who knows. Nevertheless, surely there must be a way to measure Schumann resonances with magnetometers so that LIGO could rule out these lightning strikes from their data. Surely. Well, LIGO did look into the issue a little bit, and they did buy a couple of magnetometers. I have the paper linked in the blog post. And in principle, only a couple. If the magnetometers measure something at the same time that LIGO measures something, that should signify that no gravitational wave has been measured. Yet, this doesn't work very well, because for many of their measurements, the magnetometers were not in operation. And when the magnetometer's data is significantly noisier than LIGO's data, they will rule out everything that LIGO measures, which tends to be the case when the magnetometers are in operation. So, the weird thing about using magnetometers to validate the LIGO detections is that magnetometers were originally used, the exact same device was originally used in initial attempts to detect gravitational waves by a scientist named Weber. There was an absolute mania for detecting gravitational waves many, many decades ago, a few decades before LIGO was proposed. But it's like they've forgotten this. The community forgot this mania and went on and built a new experiment based on a dead principle. It's as though Weber's ghost is making a reappearance whenever they try to validate their measurement with magnetometers. So what happened was, around the world, people started building these magnetometers and claiming that they were measuring gravitational waves. But after getting enough statistics, because they're relatively cheap devices, you had labs all over the world claiming that they were measuring gravitational waves, but the timing didn't match up. And that meant that they were all measuring noise. And they proved this statistically. But the trick about LIGO is that there's only one device like it. So it's much harder to practice the scientific method and compare. You need 100 LIGOs so that you can get enough statistics to see when you're measuring noise. And even if you had 100 LIGOs, you still couldn't distinguish between a signal that was originating from the sun or Jupiter and something that's coming from deep space. It just doesn't work. Or something coming from the Earth. Okay. So deluded and scam science lives on, and Weber's magnetometers are used to validate it. How ironic. I would feel sorry for the scientists involved in this project, but whenever I've engaged with them online, they've been rather rude and obstinate. But then again, how would you feel if you found out that the project in which you'd invested decades of your life was a terrible idea on every level? Epistemological, just everything. I literally look at this experiment at every level, the theoretical level, the technical level, all the way down. And you find fundamental errors in thinking at every level. So if you found that your project was a terrible idea, do you just roll with it? Or do you go crazy and just start breaking everything in sight? And I'm sure that there are people who are very paranoid that this is the reaction. What happens when a hamster is removed from his hamster wheel for the first time in his life? Does he go crazy? I don't think so. I think he takes a nap. Really. Take a nap, paint a picture, look at some flowers. It's a lot nicer than staring at signals on an oscilloscope or noise, studying noise. It's a lot nicer than studying noise, which is, by no chance, is the theme of my first novel. It's about the limitations of the scientific novel and what happens when people get lost in noise. It's supposed to be funny. Thank you for watching. Until next time, please tune in for my next video.